So before you start the simple oscillator basics worksheets, I want to go over just one quick thing, or a few, I guess, to just summarize the things that you know so far. So first of all, equilibrium, this is going to be where the thing is going to want to be naturally. So that's going to be where it would be sitting on the table without stretching or squishing it. That means that that's where the force from the spring is going to be equal to 0. The spring's not pushing it to the right, it's not pulling it to the left, it's just sitting there right in the middle. And this is important because that means that if you're not pushing on it, if I had my net force equation, well, the only force is acting on it in the x direction is just that spring force. And we know that that's equal to mass times acceleration. Well, that means that at this spot at equilibrium right here, my acceleration is going to also be 0. And by the same token, if I then stretched it to its maximum position, by the way, this maximum position, the farthest it gets, this distance is your amplitude. So my maximum displacement is my amplitude. Displacement, or x, is going to be wherever it is. It could be here, it could be here, wherever it is at any moment in time is going to be x. But amplitude specifically describes your maximum displacement when it's oscillating. All right, so if we know that amplitude, then that's going to be where the force is going to be the biggest. And we know that the force from a spring, according to Hooke's law, the force from a spring is kx, which means that if you know the amplitude or the distance that this thing gets stretched, you then can figure out the maximum force. And if you know force, you can put that here and just say, force from a spring is kx. That means that's equal to my mass times acceleration. If you know the mass of the block that's accelerating, then you can find that acceleration. If you are given the period, you would know the frequency and vice versa. So period is capital T. That's the time it takes for the block to go from, let's say, from here all the way to the maximum and back again. And so period is that amount of time. Frequency is how many oscillations per second. So that's 1 over the period. And the same way, the period is 1 over frequency. So just if you know period, then you know frequency. If you know frequency, you know period. One more thing, we haven't said anything about velocity yet. Well, we've just finished going through conservation of energy. Well, at this point in the middle, at equilibrium, our spring potential energy is 0 because the spring is not stretched. And by the same token, then, at this maximum position, this is where our velocity is 0 because it is not moving any farther to the right. It hasn't started moving to the left, so our velocity is 0. And our spring is stretched the most. So that means that, yes, our kinetic energy is 0, but our spring potential energy is at its maximum. So what we're going to do is when we're doing velocity, we're going to use conservation of energy. And the reality is we could do conservation of energy to find the velocity at any point or at any displacement. All we needed to know is the displacement, because then we can find spring potential energy. And if we know spring potential energy, we can find our velocity using conservation of energy. And then the only other thing to know is this equation for the period of a spring is 2 pi times the square root of m over k. So if you're given the period or you're given mass, if you're given 2 of these things, you can solve for the third one. And this is basically the same as the period of a pendulum, but period of a pendulum is 2 pi times the square root of L over G. All right, so we're going to take it from there, and then I'm going to work through the worksheet with you.